Hi, we're Team Biochar, a multidisciplinary senior design team from Kate Gleason College of Engineering. This is us here standing in the APC lab where we conducted most of our testing. The problem that we were presented with by our parent company, Sintrust, was to redesign the plant pot material so that it's able to have mechanical properties similar to that of polypropylene, but have significantly less carbon impact on the environment. And to do this, we were tasked with taking two different types of biochar and incorporating that into a plastic and biochar master batch, and then running tests with it.
So the first part of our project was to actually design the experiment that we would be conducting once we got into the lab. And we did that by, like Andrew said, using two types of biochar feedstock, wood-based and wastewater-based. And then for each feedstock type, we varied the weight percent biochar from 10 to 25%. And we did a control batch for a total of 9 batches to find our ideal composition. So once we actually got in the lab, we split our production into 2 phases. In the first phase, we crushed up our biochar. We produced our 9 different compositions using a heated mixer and a heated press. And then we picked our favorite of the compositions based on testing performance from, tensile testing, hardness, etc. And then in phase 2, we produced a larger batch of our favorite composition using the twin screw extruder, and then we pelletized that material.
The ideal composition we landed on was a mixture of 25% sludge-based biochar, 59% polypropylene, 15% calcium carbonate, and 1% MAP, and with a biochar particle size of between 425 and 104 microns. Since the tensile strength and Young's modulus were pretty competitive across each of the batches, we were able to prioritize biochar content for our decision, thus leading us to a roughly 50% reduction in carbon footprint compared to base polypropylene. We did make a few attempts to thermoform our ideal composition into a plant pot. However, due to time constraints, we were unable to fine-tune the conditions necessary for a successful thermoform.
Looking at a conclusion of our data, we were able to get a 47% decrease in our carbon footprint compared to base polypropylene, which was our overall goal. And although our tensile and Young's modulus did decrease by a significant amount, we also saw increases in our impact resistance and hardness. In conclusion, although tensile strength weakened compared to base polypropylene, we still believe this material in low load applications is an effective way to minimize climate change. Thank you.